Hello, and welcome to the lesson on the definite integral as a limit. This video was created to accompany the handout of the same title from class. As an introduction to this topic, we'll use a limit to find the area under the curve with the equation f of x equals 25 minus x squared from 0 to 5. The graph is a parabola that opens down from its vertex at 0, 25. This area would be represented as the integral from 0 to 5 of 25 minus x squared dx. The width of the interval from 0 to 5 is 5 units. If we separate this area into n rectangles of uniform width, then each rectangle will have a width of 5 divided by n. The height of each rectangle will be found by f of x. If we use right-hand rectangles, the x value on the right side of the first rectangle is 5 over n. So the height of that rectangle will be 25 minus 5 over n squared. The x value on the right side of the second rectangle is 5 over n times 2, and the height of that rectangle is 25 minus 5 over n times 2 squared, and so on. In general, the height of any rectangle under this curve will be 25 minus 5 over n times I squared, where I is 1 for the first rectangle, 2 for the second rectangle, 3 for the third rectangle, and so on. So this is what the sum of the areas of the n rectangles under the curve would look like. In sigma notation, that's the sum from I equals 1 to n of 5 over n times 25 minus 5 over n times I squared. So to evaluate this sum, first we'll simplify, and then I'll separate the difference into two different sums and factor the constants out of the sigmas. So here, anything that's not an I is a constant. From your work with series in Algebra 2 and Pre-Calculus, recall the formulas written in yellow for the sum of the first n terms of a series with constant terms, C, and for the sum of the first n terms of the series, 1 squared plus 2 squared plus 3 squared and so on up to n squared. I'll use these formulas to replace the sigma expressions. And then I'll find the limit of this expression as n approaches infinity. So this will represent the limit of the sum of an infinite number of rectangles drawn under the curve. To find this limit, I'll separate and simplify. And the first limit goes to 125. And using our rules for horizontal asymptotes, we have equal degree in the numerator and denominator of the second limit, n to the third over n to the third. So that goes to 125 times 2 over 6, the ratio of the coefficients. Thus, the sum of the areas of an infinite number of rectangles drawn under the curve is 250 over 3. In number 6 on the handout, we're asked to use a limit to calculate the area under f of x equals 2x minus 2x squared from x equals 0 to x equals 1. The width of the interval is 1. And for n rectangles drawn under the curve, the width of each rectangle will be 1 over n. The height of each rectangle will be f of 1 over n times I. So 1 over n times 1 for the first rectangle, 1 over n times 2 for the second rectangle, and so on. Then the area of each rectangle is base times height, or 1 over n, times 2 times I over n minus 2 times I over n squared. We need the sum of the area of the n rectangles. So to evaluate, again, I will simplify and separate, and I'll factor out anything that's not an I, because those are constant. So again, I will use the formulas from Algebra 2 and Pre-Calc to substitute in place of those sigmas. And we'll find the limit of this sum as n approaches infinity. This limit goes to 1/3. So the area under the graph of f of x equals 2x minus 2x squared from 0 to 1 is 1/3. The way you may see this concept addressed on the AP exam is shown in problem number 7 on the handout. I'll do letter A with you in the video, and then you'll have to do B and C on your own as an exercise. In 7a, we're given the limit as n approaches infinity of the sum from I equals 1 to I equals n of 2n times 2 over n times I squared minus 2 times 2 over n times I. Most likely, the 2 over n multiplying on the outside must represent the width of each of the n rectangles. This means the width of the entire interval must be 2 units. So we'll label the limits of integration 0 to 2 to make the interval have the given width. The other part of the expression must be the height of each rectangle. Thinking back to how we found our answers for the first two problems, notice that the values we input in place of the x to find the heights were the width of the interval times I. So the inputs here must be 2 over n times I. That means f of 2 over n times I is 2 over n times I squared minus 2 times 2 over n times I. That translates into the function f of x equals x squared minus 2x. So this is the function under which we're finding the area. That makes our integral expression the integral from 0 to 2 of x squared minus 2x dx.